If you haven't done so yet, make sure you pause the video and try to answer the question again first on your own before listening on. We've gone ahead and drawn a picture to represent the information given in the question. We have a current equal to 15 amps that is directed along the positive x-axis. So we have symbolized that with a purple colored vector showing the current pointing along the positive x-axis. We then have a magnetic force per unit length of 0.12 newtons per meter that's acting on this conductor, and it's acting in the negative y direction. So we have drawn a magnetic force pointing straight down in the negative y direction. We are then asked to calculate the magnitude and direction of the magnetic field. Now it turns out that when a straight conductor of length L carries a current, we can determine the magnetic force acting on it using this equation right here. We have the magnetic force, we have the magnetic field, which is B, the current I, the length L, and then the angle between the current and the direction of the magnetic field. Hopefully we will be able to see that the angle between the current and the magnetic field will end up being 90 degrees. In fact, let's take a look at that more closely. What we have done over here is we have drawn a right hand. We are applying what is known as the right hand rule. With the right hand rule, you want to arrange your hand in a flat orientation, and you want to point your thumb in the direction of the current. The palm of your hand will be pointing in the direction of the force, in this case downward in the negative y direction, and then your four fingers will naturally be pointing in the direction of the magnetic field. Hopefully we can see that in this case the magnetic field, since the fingers are pointing along the positive z-axis, will also be pointing along the positive z-axis. So if the current is along the positive x-axis and the magnetic field is along the positive z-axis, then the angle between them will be 90 degrees. So keep in mind that theta in this problem is indeed 90 degrees. Now, back to the problem. We're going to rearrange the given equation so that we can solve for the magnetic field strength. Let's recopy it over here first. And in order to isolate the magnetic field, we will divide both sides by the quantity IL sine of 90. They'll cancel out on the right-hand side. So now we can see that the magnetic field strength, B, is going to equal the force divided by IL sine theta. Now again, theta is 90. The sine of 90 is 1. So on the bottom, you actually just have IL times 1, which indeed is IL. So it might be convenient to just discard the sine of 90 at this point. Now, because we are given the force per unit length, we have to kind of look at this equation very carefully. It will help to rewrite it one more time, but perhaps we will be careful to kind of circle this quantity. This is known as the force per unit length right here. And that was the quantity given in the question. In fact, we could rewrite it one more time if we wish as force over length and then put that over the current. So this would be a mathematically equivalent expression to the one above it. We can now simply plug in the known values. The force per unit length was given in the question as 0.12 newtons per meter, and the current was 15 amps. So we'll have 0.12 newtons per meter divided by 15 amps. When you work this out, you're going to get 0.008, and then the standard unit of magnetic field is Tesla. So this would be the correct answer to the first part of the question. The second part also wants the direction of the magnetic field, but we have already explained using the right-hand rule that the magnetic field will be pointing in the positive z direction. So that would be the correct answer for the direction of the magnetic field.